Swayam Prabha. Digital India. Educated India.
Now, looking into this point, if we try to see, we had the other condition where we had said in the Kuntakar condition that Gj should be less equal to 0, and if we try to fit in this particular solution for the two different constraint, we'll find that this point violates the first constraint, however it satisfies the second constraint. So in that case we can say the Kuntakar condition is not satisfied at least for one of the constraint, and hence we cannot use this solution. And the same applies for this case A as well. Now let's look into the case C. In the case C, we said that the first constraint is active and the second one is not, which means now this is active, this is not. And if we say so, then our obtained solution is this value, which is x1 is equal to 0.781 and x2 is 0.239, and if you look into that point is going to be somewhere here, which is part of the same objective function contour value, which is here. Now in this point, if we try to see the Kuntakar condition, again my condition related to the constraint, one of the constraint is satisfied but not the other. So in that case again we say that my Kuntakar conditions are not satisfied. So that goes out my case C. Now we are left with the last case, which is case D, and in this case we said both constraints are active. And if we say both cases are active, we obtain the value of the design variables as 0 and 0, which is exactly this point, the point where my constraints meet each other. And there is only one point where my constraints meet. So this solution is feasible solution, because if we try to see the constraint requirement, which is this criteria, we'll see that both constraints are met. However, it is the only point, and in this particular point we cannot say whether it is the maximum or the minimum, because it is the only, in this case maxima is equal to minima. Since we cannot decide whether the solution is the maximum or minima, that's why when we estimated the lambda values or the Lagrange multiplier, we found that both the values were 0, which means both can take either positive, indicating that it is the minima point, both can take negative value, indicating that it is the maximum point. So we are not in a very clear situation where we can say it is a maxima or the minima. In other words, the Kuntakar's conditions is not giving me the definite answer for this particular problem, but we know that we have reached a solution which is satisfying the Kuntakar conditions, at least with respect to the constraints. However, with respect to the lambda values, we are still indecisive on this particular point. If you understood this process clearly, I have a few practice problems for you. In this practice problem, again we are looking into the same objective function, however my center now lies at 0 and 0. You can follow through the same steps which I have done in the previous two slides to see how your result is going to be, and the graphical representation of this particular problem is this. You can actually plot your solutions and see where it lies and how you can decide and what is your decision on the solution. Similarly, I have another practice problem. In this practice problem, we are using the objective function which we had used in the example I have shown you. However, my constraints are slightly different, making it little bit off, and now we have multiple points where my constraints are meeting each other. And as I said, my blue line represents the first constraint. So the first constraint, if I look into the infeasible region, that part I am marking it. And in a similar way, for the second constraint, if we mark the infeasible region, which is going to be like this. It leaves out to be the area, this part, as the feasible region. So as long as my search is within the feasible region, we should get some solution. And in this particular problem, you can clearly see my minimum point lies at 1 and 0, so which is inside the feasible region, but not on any of the constraints, indicating that none of the constraints are expected to be active, but both constraints are going to be satisfied. If constraints are not going to be active, means my lambda values are going to be 0. So it is the same option which we had in the previous, but my constraints are going to be satisfied. So just try to solve the problem using the steps and see how you conclude about the obtained solution. Now this same problem I am going to change little bit for another practice problem. In this case, I am changing the sign of the constraints from lesser equal to 0 to greater equal to 0, and once we make this change, my feasible region for each of the constraint is going to change. Now this part becomes the infeasible for the first constraint, which is represented by the blue line, and for the second constraint, which is represented by the orange line, this part becomes my infeasible region. So this enclosed part, which was earlier feasible, now becomes infeasible. And if we try to identify the feasible region for both constraints, we are now seeing that this is my feasible region as well as this is my feasible region. And if both constraints are active in this minimization problem, then we have one solution here and another solution here, and from these two we have to decide which one is going to be the minimum. By looking at it, we can say this one is the minimum and this one is the maximum, relative maximum compared to this. When both constraints are active, you can follow through the process and see how you can decide about these 2 points. Now in the Kuhn-Tucker conditions, we discussed about the inequality constraints. However, in real world engineering problem, you can always have both inequality constraints and equality constraints. So now we are going to see how you can solve problems with both inequality constraints and equality constraints. And in this case also, we are looking into the Kuhn-Tucker conditions for those type of problems. So the multivariable optimization problem with both inequality and equality constraints is going to be like this, where my objective function is going to be either minimized or maximized, and this objective function is for the n number of design or decision variables, and this objective function is also for the constraints, the inequality constraints of this nature, where I have m number of inequality constraints and as well as the equality constraints of this nature, which you have seen in case of Lagrange multipliers, where I have p number of equality constraints. Now this particular problem, if we want to look into the necessary condition as per the Kuhn-Tucker conditions, then we can represent that in this form. Here the first equation, which is going to give us n number of equations, represents the partial derivative of the Lagrange functions, which includes both equality and the inequality constraints. The second set of equations, which is of m numbers, is going to represent the Lagrange multiplier multiplied with the inequality constraint, indicating both active and inactive inequality constraints. The third one, again of m number, is going to represent the inequality constraints, whether this is going to be satisfied or not for the solution which we are obtaining, or for the extreme point. The third one, which is of p numbers, are going to represent the equality constraints. And the fifth, which is our Lagrange multiplier of m numbers, are going to represent for both active and inactive inequality constraints. So this is for active plus inactive inequality constraints. In this case, both lambda and beta are Lagrange multipliers. This one is for the inequality, this one is for the equality constraints, and we can use this to solve the problem and see whether the Kuhn-Tucker conditions are satisfied or not. So now let us look into the solution process through an example. In this case, we are using the same objective function from the earlier example which we had solved, circles which has the center 1, 0. However, the constraints are slightly different. In the first case, the constraint is inequality less than equal to 0, and in the second case it's an equality constraint, and you will see slight variation in this x2 term, which we have a value added to that, and in this case a value subtracted to that. Now the solution process will follow through the same process, same method, where we are considering that we have unknown active constraints, means we do not know the active constraints, so we are considering both active and inactive constraint, and for that purpose we have to first explore, or first we have to obtain the partial derivative of our objective function, inequality constraint and the equality constraint, and accordingly we have to represent it in the equation of this form, where we are taking up the first term of the objective function's partial derivative, the first term of the inequality constraints partial derivative, and the first term of the equality constraints partial derivative, and this is the Lagrange multiplier for the equality constraint, and this is the Lagrange multiplier for the inequality constraint. And if we transform it or simplify it, we can represent the equation in this form, which I am indicating as equation 1. For the second terms of the partial derivative, we can write the equation in this form, and after simplifying we can rewrite the equation in this form, which I am calling it as equation 2. Now we have the inequality constraint, and in the inequality constraint we said if we multiply with the Lagrange multiplier with the inequality constraint, that is supposed to be equal to 0. So this is going to give me the third equation. Likewise, the equality constraint needs to be satisfied, so we are writing the equality constraint here, and this equality constraint, if we simplify, we can obtain the x2 value of this form, and this is my equation 4. So we have 4 equations and 4 unknowns. Now we'll start trying to solve or try to find out the values which are going to satisfy for these 4 equations. So in the first step, we considered that my inequality constraint is inactive. So we can consider lambda 1 is equal to 0, and then we start solving it. From equation 2, we can easily obtain the x2 value and correlate with the x1, the other design variable. So this is the function which I am going to get. Now from equation 1, I can replace the h1 with x2 values and subsequently replace with the x1 values which we obtained here. Then we have the equation which is of x1 term only, and this is going to be the third order polynomial of this nature. If we try to find out the real root of this design variable, we can obtain the value x1 as 0.813, and if we replace it in this equation, we can easily obtain the x2 value as negative 0.230. So this is one of our values. Now let's look into the other condition. So other condition could be my inequality constraint is active, which means my lambda value is not equal to 0. If my lambda value is not equal to 0, then the other part of the equation 3, which indicates my inequality constraint, that has to be 0, indicating my solution lies on that inequality constraint. And if we make it 0, we already have the other part of the constraint, which is equation 4, which is supposed to be 0 because that is the equality constraint and solution should lie on that equality constraint. So if we try to solve these two equations, we can easily obtain my x1 value. The two roots of this x1 value is going to be plus 0.447 and minus 0.447. In either cases, the x2 value is going to be 0. So we have eventually two different points from this solution. One is 0.447 and 0, and the other one is negative 0.447 and 0. And from here we have one point which is 0.813 negative 0.230. So altogether we have 3 points. Now we need to test whether it has satisfied the constraint requirement, whether lambda values are good enough to decide whether we have reached the optimum point, the minimum or the maximum. For that, we'll go to the next step. In this case, we are testing the optimality, and for the first point, as I said, the first point was 0.813 and negative 0.230. the inequality constraint is going to be violated in this particular case. So we can conclude that this is not a feasible solution. So the inequality constraint, which was Gj less equal to 0, so it was violating this constraint, and hence this is what it is happening. The second point, which is 0.447 and 0, in that case we are finding my lambda value is going to be positive, and if it is positive, we know that the function value is expected to be minimum and the point is representing the minimum point. So my function value, minimum function value, is going to be 0.305 if we replace x1 and x2 in my objective function. The third point, which we have negative 0.447 and 0, there my lambda value is negative, indicating the point as the optimum point or the maximum point, and the function value is going to be maximum, and the maximum function value is 2.093. So at this particular point we are getting the maximum function value, and this particular point we are getting the minimum function value. Now let us look into the graphical representation of the three obtained solution for better understanding. Now in this case we have the two constraints. The first constraint is less equal to 0, or the inequality constraint. Again it is represented by the blue line. So inequality constraint means this side is my infeasible region and this part is going to be my feasible region, whole complete part. So for the second constraint, which is of equality nature, my orange line, my solution should lie along the orange line because it's an equality constraint, neither on this side or nor on this side. So if we really look into this particular, since this part is my feasible region for the blue line and my orange line is the feasible solution, so we can say from this point of the orange line to this point of the orange line is going to be my feasible solution range, which we need to check where we can obtain the minimum value. And as I said, my objective function, which is convex in nature, is going to be minimum at this point. And if we look into the 2D version of it, we are saying that this is my feasible solution range and these are my contours of my objective function value. So we have to find out where the objective function value is going to be minimum, and we had tested two conditions. In the first case we considered my inequality constraint is inactive, which means it has no role to play, indicating my complete orange line is my feasible solution range. And in that case, when we tried to solve the problem, we got this point, which can be represented somewhere here as my solution point. And if we again draw the circle, it is going to be somewhere like this. So if we try to test this particular point, obviously it is going to violate my inequality constraint because this part is infeasible region for my inequality constraint, and this particular point which we obtained as a solution lies in that infeasible region. Now in the second case, which is case B, when we said the inequality constraint is active, which means my solution is supposed to lie along the orange line and as well as the blue line. So we see that there are two feasible locations where it can be true. So that is point number 1 and this is point number 2. So this is point number 1 and this is point number 2. In these two positions we have to check. So first point we obtained 0.447 and x2 equal to 0. So this is my point number 1 representing, and the second point is this, which is 2. Now if you recall, we said at point number 1 this one was minimum, and it is clear from here the objective function is going to be minimum here and the objective function is going to be maximum here. So this is going to be the maximum. So this is how we can understand the solution for the two variable. Of course it is going to be difficult visualize the solution if the number of constraints increases more than 3. Well, in today's class we actually saw how we can use the Kuntakar's conditions to solve the multivariable optimization problems with inequality constraints. In this solution process we do not need to worry about the active or inactive constraints. We do consider all the constraints and investigate various situations and identify whether the obtained solution is the maxima or the minima. In this process the solutions were quite easier to solve and we could graphically understood what the solution means. Now in this process we saw that when the number of constraints and when the number of variables are lesser, we can easily do it manually. However, once the number of constraints and the number of variables increases, it may not be the case. And another important thing, if you recall, I indicated that the Kuntakar conditions is applicable only in case of convex optimization problem, which means my objective function as well as the constraints need to be convex. If these are not convex, the Kuntakar condition is not applicable. Now the real world engineering problems are not always going to be convex, or it is very difficult for us to prove that the problem is convex. So in those cases it is not easy to use the Kuntakar condition unless we reasonably approximate the real world engineering problem into a convex optimization problem. So for those cases or for the complex optimization problems we do need to use the numerical methods of the solution, and from the next class onwards we'll be discussing about the numerical method of the optimization problem. So till then, thank you and see you in the next class.